All right, so here we're on 11.5 on absolute maxima and minima. So we're going to obviously look at the absolute maxima and minima and look at the second derivative and extrema. All right, so one of the most important applications of the derivative is to find the absolute maximum or minimum value of a function. So in this section, we're going to develop the procedures needed to find the absolute max and min values of a function. So by definition, absolute maxima and minima. So if we have some c, the f of c is going to be greater than or equal to f of x for all x in a domain of f. Then if that's the case, then f of c is called the absolute max of f. Now, if we have some c and f of c is going to be less than or equal to all f of x for all x in the domain of f, then f of c is going to be called the absolute minimum of f. Now, an absolute minimum or maximum is called an absolute extremum. All right, so these are some examples where we have them and we don't have them. And so in A, we have no absolute maximum or minimum. And that's because, as we notice, these keep going down and up. Now we have local maxima and we have a local minima, but we don't have the actual absolute. Now, in a case of like a parabola here, we have an absolute max. So that's going to be the absolute max. Now, we don't have an absolute min, but we have the absolute maximum. Now, if we look at this one, we see that we have an absolute minimum, but we keep going up on each direction, so there's not going to be an absolute maximum. So it depends on how the case is on what you're going to have. So in many applications, the domain of a function is restricted because of practical or physical considerations. So maybe cost or revenue, you're not going to have negative values, things like that. So prices and quantities can't be negative. You can't produce negative number of things. Now, they also cannot produce an arbitrary large number of goods. So there's going to be kind of the absolute maximum that they can actually make. Now, if the domain is restricted to some closed interval, as is often the case, then we have this following theorem, theorem one. A function f is continuous on a closed interval, so a to b, and it's closed. We have in brackets, so it's going to be a dot. Well, it's going to be a dot, and then it's going to be something, and it's going to be another dot. And so there's going to be, some kind of endpoints. Has both an absolute maximum and an absolute minimum on that interval. And that's because this could be our absolute minimum here, and this could be our absolute maximum here. Now, these could be, your local max, and that could be maybe your local min, depending on how it goes. But you're going to have absolute min and max on that restricted interval. Okay, so it's important to understand the absolute maximum and minimum depending on how both the function and the interval work. So some examples here, kind of like I was drawing a little bit before, not so well, but on this first one, we have an interval from 2 to 12, and we have this function. Now, this is the same function for all of them, so that's the function we're looking at. But from 2 to 12, it looks like this. And we have this absolute minimum here, and we have an absolute maximum here. Now we've also got a local min and a local max, but we've got the absolutes as well. Now, if we restrict our interval from now 4 to 10 instead of 2 to 12, now the maximum absolute is right here at the 5, and our absolute min is here at the 9. And so then we can see we have the absolutes at different places than we did on the interval 2 to 12. Now, if we switch it even more to 4 to 8, then our absolute max is still going to be the same as it was here, but our absolute min now is going to be right here. So it's going to be at the 8. So we have differences depending on how we restrict our domain here. Now, if we go over here, this is going to be kind of an unusual one. Now we have restricted from 3 to 11, and we notice 3 and 9 have the same. They're both absolute minimum. And f of 5 and f of 11, they're both the same. They're both absolute maximum. And so sometimes you can have multiple, and so you're going to have to actually test them. And so that's going to be kind of a key thing to think about as you're working through these problems. Now, locating these absolute extrema, if they exist, must occur at critical numbers or endpoints. Remember, endpoints, they were the end ones. Now, that was an end one, but this was inside the middle, so that would have been a critical point. And so we have all these different things we have to look at. So critical numbers, if they exist, must lie in the domain of the function, so they can't be outside of that. And so if our function is restricted to A to B with, endpoints, then C has to be within that range. So C has to be within that range A to B. Now, how do we find them on the closed interval? Well, first check to make sure that f is continuous over that interval a to b. And so, if you have something like we had before, something like that, make sure it's continuous and doesn't have some kind of a break or something like that. Then we need to find the critical numbers in that interval from a to b. Now we're looking at just the critical numbers, not the endpoints then. And then we evaluate f at the endpoints and at the critical numbers found in step 2. And then the absolute max is going to be the largest value we find, and the absolute min is going to be the smallest value we find. And so that's how that's going to be played out when we're doing these. And so what we'll do is we'll pause here, and then we'll come back and we'll actually do some calculations and find absolute max and absolute min.